what we're going to be going over here is multiple linear regression, and we're going to be looking at model testing here for our regression model. So we'll start out by looking at some plotted points here on an XY coordinate graph here. So along our x-axis, this is going to be our independent variable here, and really you're going to have two of them, x1 here and x2. And then along our y-axis, that's our dependent variable here, and we just have dependent variable y. So dependent variable y here depends on whatever values we have for x1 and x2 here. So first off, just looking at our plot here, we're going to have two different data sets here that we're going to be looking at. The first data set is A here, showing by those little red squares here, and that's our x1 independent variable here. And then our second data set is going to be our data set B here, and that's showing by these blue circles here, and that's our x2 independent variable here. So just going and doing a linear regression here, just plotting them separately here for our data set A here represented by x1, we got this green line here, and that's really the line that this line represents those red squares here, and that is equal to 10.3x here plus intercept of y-intercept here of 300. Okay, so it's got that slope here, and that's where we just did it separately here. We just regressed our x1 independent variable against our dependent variable y here. Okay, and then we have our second line here showing by this blue upward sloping line here. And this is a separate regression here, just taking our x2 independent variable here and regressing it against our y dependent variable, and we come up with this equation here, 54.4 here, x2 times x2 here, whatever x2 value we have, plus a y-intercept here of 389. Okay, so that's just looking at them separately here to get an idea of what's going on. But now, we're going to combine these two data sets here. Data set A represented by x1, independent variable here, and data set B represented by x2. And we want to know if, by combining these two data sets here, we're going to be able to come up with a relationship between the two here that's going to better represent our dependent variable here, y here. Okay, so combining the both sets here, I did a multiple regression here by data set x1 plus data set x2 regressed against our y dependent variable here, and we came up with this equation here, 7.6 x1, that's the slope of our line here. And this is with the multiple regression here. I'm showing with that dotted dashed line here in green versus what we had done when we just did the separate one here for x1. And that was what? The slope here is 7.6 times x1 here. And then with the second, that's for data set A, and then for data set B, that is the multiple regression was 37.8 times x2, and then they have that y-intercept here of 42. So this dashed dotted line here for with our multiple regression here for B is represented by the slope here, 37.8 times x2 here. Okay, so that gives us a little picture of what we're talking about here when we looked at our single regression here, a separate regression, versus our multiple regression. And you can see how it changed our slope here, but we're going to look at this in 3 dimensions as well. But to get a little better feel for it again here, if we just looked at these ratios here, so remember with our initial, when we've done them separately, we have the slope here of 10.3 for our x1 variable here, and then 54.4 here for our x2 variable here. And that gives us, just dividing that out, gives us a ratio here of 0.190 or 19% here, looking at x1 versus x2. Okay, but when we did our multiple regression, we're going to come up with a very similar ratio here. So if we look at our regression here, well, if multiple regression for our data set A here, our x1 was 7.6, and we divide that by our data set, or our x2 variable, or data set B here, 37.8, we come up with a very similar ratio, or 0.20 here. Okay, so that sort of gives us a feel what's going on here when we did the multiple regression. Just remember, this is the equation with our multiple regression, and we're going to test this equation here to see if it is a viable equation, and if this multiple regression equation here is better than just looking at these two variables separately here. So looking at x1 here separately versus x2 here separately. So we want to find out if that multiple regression is going to give us a better estimation of what our y-dependent variable is when we combine both x1 and x2. Okay, so that's just looking at our xy coordinates. Now let's move over here. Just get an understanding of what's going on here when we do this computer modeling or the software model here to come up with a regression, and what we're talking about, a multiple regression. So let's just look at it in a 3D space or a 3D plot here. So we've got these two independent variables here, x1 and x2, and they both have a different scaling factor here. The x2 goes from 0 to 20. x1 is 0 to 100 here. And this is, then we got our y1, our dependent variable here, which goes from 0 to 2000, just to give you an idea. So, gone out, plotted those 12 different data points here, and each one of those data points has three coordinates here in 3 dimensions, an x1, x2, and a y coordinate here. Okay, so that's what the computer is starting with here, and we want to come up with a regression line that's going to, a multiple regression line is going to represent these 12 points here in really 3 dimensions here. So this is what the computer come up with here. So we did that multiple regression with those these two independent variables, x1 and x2, and against our y dependent variable here. And remember, we come up with the regression with the numbers I had come up 7.6 x1 here. So that x1 here, that's the slope of this line here. That's the slope, 7.6 x1. The slope based on our scaling factor here, 1 to 100. So for each increment that we go, our y here, that explains our y here. So if we go over 1x here, we go up 7.6 here in our y here. But that's based just on that first independent variable here, x1. But then if we look at our second independent variable here, x2, we got a slope here of 37.8 shown here. So every time, and remember, this scaling factor is a little different here. It goes from 0 to 20 here in this case. So every one increment we go in x2, we're going to go up or represent our y increase here by 37.8 here. Plus we got that intercept here of 42 near 0 here. So really what this computer program has done here, it's set up a linear regression here, and it's really looking at the points on this plane here. So any point on this plane here represents what our y value, or our dependent variable, would be based on whatever point we're sitting at with x1 and x2. So it sort of gives you a feel of what's going on here and what the computer had to do here. It had to take all those data points, or your software package, it took all those data points and then it fitted a plane, a linear plane, through those different data points. So 3 points represents a plane, and then the other thing is, just remember, any point on this plane here, we had as an x1 value, has an x2 coordinate here, and that gives us, it also has the y coordinate. So we're explaining our y independent variable here by looking at both x1 here and x2 here. Okay, so that's really what we're looking at when we talked about this multiple regression here. All right, and if we go down here and just look at it in terms of just our x2 independent variable here, that 1 to 0 to 20, just looking at it, moving right in, slashing right through that plane here. So that our model has got some linear line that went through here in our x2 direction. Again, trying to represent what our y independent variable y is here. And then over here for our x1, same thing. Looking right into our x1 axis, we got the data point showing here. Okay, so what this model has to do here, it took these, both our x2 and our x1 independent variables that come up with this 7.6 here x1 plus 37.8 here in x2 plus that 42 here. So you can see sort of what's going on here with when you look at it and what you understand what that computer software package is doing when it's doing the linear regression here. It's coming up and it's slicing through all these data points here and looking both at the x2, x1, and the y, and it's coming up with really an average or a least squares between all those different data points, and it's coming up with the slope. So this is what you're working off when you have looking at this multiple regression. So the question is here, are we better off with a multiple regression here looking at it in 3 dimensions here to predict your y value with both looking at x1 and x2, or are we better off just looking at x1 separately to determine our y, predict our y, or x2 separately to predict our y? So this is what we're really going to be testing for here. Okay, so let's go down and let's look at our tests here. So again, this is the question. Are our x1 and x2 correlated? That is the question we have to answer here. And really, we don't. Okay, we want to, they against each other, we don't want them correlated here. And we'll go through and look at what we're doing. So for our first test, we're going to do a correlation matrix, check for multi-collinearity here. So really, I just did it in terms of our Excel statistical package here. And you would select data analysis here, that Excel data analysis package, and then you'd select the correlation underneath it here. And what we're going to do here, and really there's 2 different correlations. There's the one here with the data analysis package, which is pretty complete, which is going to give us our correlation matrix, as they call it here, for multi-collinearity, versus just the correlation itself here. The equation equals, Excel equals CORREL here, and then you have 2 different arrays here. C1, our first independent variable here versus our second independent variable. And that's going to give us some correlation here between our x1 here and x2 independent variables here. That's just for our correlation. But let's look at the data analysis correlation here. So you put in all those different numbers, the y, 12 points here for y, 12 points for x1, and 12 points here for x2, based on the requirement here for the data analysis under correlation. And you hit the button here, and it's going to give you this matrix here. And let's understand this matrix here. So we got along our column here, we got our y dependent variable, our x1 independent variable, and x2 independent variable here. And then, of course, across our top here, we got y dependent and x1, x2 here. So what we're looking for here, when we did this correlation matrix, we want both x1 here and x2 to correlate very closely, or give us a high correlation to our y-dependent variable here. And you can see that it did here for x1 and x2. x1 was correlated with y-dependent variable 0.72 or 72%. x2 here is 0.69 or 69% here. So that's what we want here. We want a high degree. We need a high degree between our y-dependent variable here and our x-independent variables here. But what we don't want is the correlation here between our 2 independent variables here, x2 independent and x1 independent. And we come up with sort of a moderate amount here, 0.39 here. But you can see it's not really that highly coordinated here, or 39% here. So you need a low degree between your x's for your independent amount here. And then you can see these ones here. You can see they're perfectly correlated. Y with its dependent with itself, x with itself here, and x2 here with itself here. Okay, so that's what we're looking at here. So really, this is the key here. We're going to be looking at an R-squared here with the Excel any software package. You're going to come up with an R-squared here for your different regressions here. And really, what is the meaning of R-squared here? If you had multi-collinearity, or you had a high degree of correlation between your independent variables here, then this R-squared is really meaningless here. But what we're looking at here is so each of the x's here, when they contribute to the regression model here, if you have a low degree of correlation. So each of your different x1s and the x2s in this case, they're going to contribute to your regression model here if you got a lower, you want that low degree of correlation here. So again, the question is our model going to be better off if we is our model defined on x1 here plus x2 to determine our y value, or just looking at x1 separately from and x2 separately to determine our y dependent variable here? Okay, so that's what we're looking for. Our first thing here was for a correlation matrix. All right, now let's move over here. We got one other correlation that we have to be working with, and we'll look at the Durbin Watson test here. And really, this is where we're just checking for serial correlation here, and I'm just showing it here. This is just understand. So you got your data here is going to go through some plus, plus, pluses, minus, 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 have some sort of sinusoidal type of function here. And then you could have the negative, that's your positive correlation here. And with the Durbin Watson, it has a zero value here. If you've got a totally positive correlation between those two different variables that we're looking at, or those independent variables in this case. And then you have on the other side, you have your negative here, and that has a value of 4 here. And that's where you got plus, 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 minus, plus, minus. And this little green line here is our regression line, and those dots represent our different points here. And then in the middle, your Durbin Watson here has got a value of 2. Now remember, the Durbin Watson here depends on different factors. I'm just using a very basic model here. The 2 here represents none. You don't have any serial correlation. Now, we do not want serial correlation here between our independent variables, because if that's the case, then we'd have some pattern here and they build off each other and multiplicative and so forth here. So for our Durbin-Watson test here with the Excel, you just put in equals sum here, sum is showing sum x, my here 2, and then you're going to have 2 different arrays here. And let's look at it here. And then you divide it by the sum of squares of the array here. So what I've done here with this model is 7.6 x1, 37.8 x2 here. We take the and plus 42, we did the residuals. You have to take the residuals from the model that we're testing here, and that's that multiple regression model here. We took those residuals here. And that's what we're putting into this equation here. So for our XOL here, the A2 goes from A2 here down to A12 for the first array here, and then A1 to A11. I'm showing A and B here, A and B. And then you divide it by the sum of squares here, A1 to A12. All the way down here. And then hit your enter and you're going to come up with a number here. Our Durbin Watson number for the set of data we're looking at is 2.494 here. So that's telling us that really we are close to, we don't have any serial correlation, either positive or negative. Actually, we do have a little bit here on the negative side here, but it's very close to 2 here. So the key is here with the 2 different tests, with this Durbin Watson test that we've done here and with our correlation matrix, we can determine here that those are x and y, or 2 different x independent variables here, x1 and x2, are really both contributing to defining our y dependent value here. So we, through these correlation tests themselves here, both serial correlation here and the correlation matrix, we're able to say that yes, the x1 and the x2, by combining them here in a multiple regression here, we should be better off here. Okay, so now let's go on and we'll move on to our next test here and looking at just an Excel spreadsheet here and understand further what the testing here of these this regression model. Okay, now let's go through our multiple regression output here and we'll look at it in terms of Excel here, and this is where we've done the regression here with independent variables x1 and x2 against our dependent variable here, y here. So starting with our r² value here, and we're with the multiple regression here, we came up with 0.71 or 71% for our r² value here. Now I've done those regressions separately here, x1 and x2 separately here against our y dependent variable, and for x1 I would have come up with 52% and x2 47%. So the key is we want to look at it in terms of our r² here for the multiple regression. So you can see here with the combining x1 and x2 into our multiple regression here, we have a much better model here. Our r² value is much higher here, 71% versus what it was here separately. And we can do that because remember x1 and x2 here have passed our correlation tests here. So this is, therefore we're saying both are contributing here to our regression model when we combine them. But what we have to test for is what they call this F test here for our variance test here, the ANOVA variance test here. So what we want to do is, it's based on an F test or F distribution here. So what we want to do here, and just go through it real quickly here, we have to come up with our F critical value here for our distribution, and that we would just through Excel equals f.inv.RT here, and then you put in your percentage here that you're looking at. We're just going to go with a 5% or 95% confidence level or a 5% rejection rate here, and then you have to put in your degrees of freedom here, and that's key point here. So in our case for our ESS here, that's the explained sums of squares here, and maybe let's go and look at that here. So what we're talking about with this regression here, we have some y mean value here for our regression here, and then we have this linear regression line we have here. So we've got our total sums of squares coming right off our each one of the points we look at. We compare that to our y mean value here, the average mean value for the independent variable here, and then the residual sums of squares, that's taken from the actual point up to the regression line. And then for the explained sums of squares, ESS here, that's coming off our y mean value to our regression line, just so you understand that. Okay, so now we've come in here and we've gone for those different degrees of freedom. So ESS, it has 2 degrees of freedom here, and the residuals has 9 degrees of freedom here. So you put that in here, percentage, your different degrees of freedom, hit enter, and you're going to get an F critical value here, 4.256 here. So this is what we have to test our F statistic against here. So just remember, this F statistic is really taking your sum of squares here for your regression here, that amount here, and or the mean sums of squares here for your regression, and you're dividing that into the mean sums, the mean sums of squares here for your residual, and you're dividing that into the mean sums of squares here for the regression or the explained portion here. And that's going to give you your F test here at 11.31 here. Okay, so what we're looking at here with our distribution curve here, just plotting it out here, we determine our critical value here to be 4.25. So that's sitting on our distribution curve here, about here. And then our actual F value have here with the multiple regression come up with 11.31 here. So we can accept that we can accept this because it's outside of the range. Had our F test here been below 4.25, we could say no, they aren't. We can't test the correlation, or the correlation is not good between that for our multiple correlation, but it's way over here, so yes, we can accept it. So it is significant and we can accept it. So that's for our F distribution here for the correlation on a regression. Now we have one other test we want to do here, and we want to be testing for heteroscedastic or non-constant variance here, just to go through it quickly. So this is the Birch-Pagan test here, and what you're going to do here, you're just testing to see if you have a multiplicative variances with our regression model, where they start out low here, the variances, and as we move up in our model here, they get really wider and wider and wider here. Okay, and that's really taking your Lagrange, you use a Lagrange multiplier here, and that's taking, it equals your R squared value. In this case, our R squared value here was 0.715 here, times 12 different data points. That's going to give us a Lagrange multiplier, LM here, of 8.58. Go to our F distribution, and again, that's sitting here over our critical limit here. Remember, our critical limit was based on 5% here on the F distribution, 4.25. We exceed that here, 8.58, so no, we don't have any non-constant variances here. So again, the multiple regression passed that test here. Okay, and then just going down and looking at our coefficients here, this is where we're going to have a T's test here. The coefficients we're talking about is our x1 or x2 variables here. There's also the intercept here, but that's really not that critical here. With the numbers that are coming up, it wouldn't be that critical here. But just understanding what's going on here, we got to come up with a T-stat, and for each one of these coefficients here, x1 independent variable here and x2 independent variable here, defined by those numbers here. So our coefficient here, intercept was what, 42 here. Our x1 here was 7.5 or 7.6 here, just understand that. And our x2 here was 37.7 here. Okay, so those coefficients, you divide them by the standard error here, standard error into the coefficients, and you're going to come up with your T-stat. In this case, our T-stat for x1 and x2, it come up with 2.7 here for x1 here, and 2.4 here for x2. So we have to compare that against a T distribution here, and we're looking at a two-tailed T distribution here. Okay, so again, going into our Excel, it's just T equals INV dot two tails here, and we use a 5% test here, 95% confidence, and 10 degrees of freedom here. And hit enter, and you're going to get 2.228 here. So that's our critical value we have to be testing on our T distribution. Remember, it's a two-tailed test here with the Excel. So our critical value here is plus or minus 2.278 here. So just looking at it from the perspective here at t-stat, for both variables we had 2.74 here for our x1, 2.47 here for our x2, and they fall outside the limit here. So yes, we can accept our values here, our coefficients here for x1 and x2 based on that test here. And if you just went up and you look at your probability here, oh, I'm just showing it a little wrong here. This is from an O1. We look at the probability here, and it should be looked at 0.2 here versus 0.02 here and 0.03, and we're much less than the 5% here. So we only have a 0.2% here and a 0.3% chance that we'd be off here. So we passed our probability test itself here. The 0.8 here, so from some old numbers here, don't use it. We use the 0.02 here and 0.3 here. Okay, so our coefficients here pass our test as well here. So we use the t-distribution here, two-tailed t-test here to test for our coefficients here and see if they're accurate we have here. Okay, so we've done our testing for the model, and our model proved out to be good here, both for correlation and also our coefficients. Okay, so that'll summarize our discussion.